In this lecture, we're going to be talking about humidity, which is an application of liquid-vapor equilibrium. And I oftentimes just abbreviate this LVE. Humidity specifically refers to a system of one condensable component and for the sake of the actual use of the word humidity, this is water and one non-condensable component. And this would be air, which is a mixture of nitrogen and oxygen. Now the same nomenclature could be used if instead of saying humidity, we instead referred to something as saturation. And this would be any mixture of liquid vapor. But generally it would refer to as a one condensable component. So for the case of humidity, we would have a system that could be filled in this case with water, and then we would have water vapor and air. If we referred to saturation of any arbitrary component, it could also be water and water vapor, but it could be, any organic or any volatile species as a liquid here. Let's say we had ethanol, and we could have ethanol vapor and air as well. And the same nomenclature that we would apply for the water system would also apply for the ethanol system. But humidity specifically refers to water. There are a couple of ways that we can express humidity. The most common one is to look at things in terms of the relative and absolute humidity. Relative humidity, this is what we understand as when we hear the news how humid it is, refers to how close to saturation it is. And this is the actual amount. In this case, it would be the actual amount of water in the air divided by the max amount times by 100. And if we were to apply Raoult's law, for one condensable component, we would have the partial pressure of water is equal to the mole fraction of water times by the total system pressure, which is equal to the saturation pressure of water. Now if we substitute this expression into the relative humidity term, we have the partial pressure of species I divided by the total pressure minus P of I times by 100. And in this case, if I is equal to water, this is what we refer to as humidity. If I is not water, we would refer to this as relative saturation. This here would represent the amount of species I, and this term here with the total system pressure minus system I is everything but component I. The other most common way to express humidity is what we call absolute humidity. Again, we can use the same nomenclature here to refer to this as absolute saturation as opposed to absolute humidity. And again, the only difference is the nomenclature of whether or not it is water. In absolute humidity, we define this as the mass of vapor divided by the mass of dry air. Air is the most common non-condensable component, but it is not necessarily the only one. You could have some sample of, let's say, benzene in argon, in which case argon would be the dry product as opposed to air, and you would not refer to it as humidity, we would refer to it as saturation. Mathematically, we can write this as the partial pressure of species I, which is effectively a way to denote its concentration, times by the molecular weight of species I, divided by the total system pressure minus the partial pressure of species I, and by the molecular weight of the dry gas. The units for this would be, in the case of water, would be maybe grams of H2O per gram or kilogram of dry air, which would be abbreviated DA. One very useful tool for doing humidity-based calculations, which can ultimately be tedious oftentimes, is to apply a psychometric chart. Now, psychometric chart is a very common engineering chart that has a lot of information, and so I want to do a quick breakdown of the key features of it so that no one was concerned about it. I'll switch to probably a pink here for color so that it can be easily distinguished from the cornucopia of colors we have already. On the x-axis, we have what we call the dry bulb temperature, and this is effectively just the normal temperature, what we would see on a thermometer or something. On this curved axis, we have the wet bulb temperature, and this is a temperature that was used back before instrumentation was as good as it is now. And effectively, what would be done is a thermometer would be wrapped with a wet rag and spun over the head. Now, what would end up happening if we're in a dry climate like Utah and Salt Lake City is, a lot of the water would evaporate, and that evaporation would cool down the thermometer inside. In contrast, if we were in a very humid environment like the southeast, there would be very little driving force for the water to evaporate, and we wouldn't have a tremendous amount of cooling, and in which case the dry bulb temperature would equal the wet bulb temperature. Now on these red lines here, we have 100%, 90% marching all the way down to 10 and 0% humidity. This is the relative humidity of water in air. And so if we had a dry bulb temperature of 20 degrees and we were to go to 100% saturated, we would have the wet bulb temperature is equal to 20 degrees, meaning we wouldn't have any evaporative cooling. Now in contrast, if we were to go, if we had a 30 degrees C and maybe, let's see, 50% relative humidity, that would correspond to a wet bulb temperature, something around 22, 23. So we'd get a couple degrees colder of the wet bulb. So on a psychometric chart, if you define two pieces of information, you have everything fully defined in the system. So if we have the dry bulb temperature and the wet bulb temperature, that would have an intersection of two lines and it would fix the point. More commonly, what you'll see is we'll define a dry bulb temperature, and let's just say a case of 30 degrees C and let's say 50% relative humidity. And we'll use this as our base case. So we'll go down here to 30 degrees C and we'll march up until we have the intersection of our 30 degrees C line and our 50% relative humidity. And this is where our system is fixed. Now from this point we can read a couple key pieces of information. We can look at the wet bulb temperature, which is not really of all that much practical importance. Actually, so we would trace it back over here. You can see you go parallel to the lines of the same color. So we could trace that back to the wet bulb temperature. That doesn't tell us a lot of information, but it's possible. The next thing that can be measured off of the psychometric chart is based on these green lines. We have the specific volume, which is the reciprocal of the density. So in this case, we have it in units of meters cubed per kilogram of dry air, and we would be about halfway in between the 0.9 line and the 0.85 line. So that would mean our density is going to be something on the order of 0.875 meters cubed per kilogram of dry air. Now if we wanted to go to a different condition, let's say some arbitrary point up here, you could then tell what the volume change was of that process. Now if we trace this line over to the right, to the yellow axis, this gives us our humidity ratio, which is a way to express the absolute humidity. In this case, our point would be about here, and that puts us at about 0.013. This would be grams of water per gram of dry air, which is a way to express our absolute humidity. And the last thing that we can read off of the psychometric chart is the enthalpy, or how much energy is contained within the air itself. And for that, we would go parallel to the white lines and trace it back over in this direction here. And that would put us at about, I don't know, maybe 65, 67. So we'll say 65 joules of energy per gram of dry air. Now if we were trying to figure out how much energy it took to heat up a stream from one temperature and one relative humidity to some other temperature and some other relative humidity, we would just take the difference between these two energies, and that would give us how much it takes. Or if we wanted to figure out what is the amount of water that is being condensed between the two, we would just take the difference between the humidity ratios there. So there's a lot of information contained within the psychometric chart, but effectively all we have to do is define 2 points. In this case, we defined the temperature and the relative humidity of 50%, and then we were able to read off the density, the absolute humidity, and also the energy contained within that gas itself. There are different types and different styles of psychometric charts, but they effectively all have the same information. Some might have a little additional, some might have a few more lines, but effectively all we would do is lock in our position by the intersection of 2 lines, and then to read the information back to the axes, we would have to go parallel based on the direction that each is plotted. So in this case, the wet bulb temperature has these slanting blue lines. The enthalpy has the slanting white, so we would just have to be parallel to those when we moved back. The yellow over here is the humidity ratio, and so all these different pieces of information can be used. The units may vary, the colors may vary a little bit, but effectively this is the general schematic for reading a psychometric chart.